Welcome to the Sleepy Engineering Channel. I'm glad you're here. Get comfortable. Settle into your pillows, adjust your blankets, and let yourself relax. Tonight, we're going on a journey through the fascinating history of human innovation, not with excitement or drama, but with the calm, gentle exploration perfect for drifting off to sleep. Each night on this channel, we explore a different technology, a different piece of engineering that has shaped our modern world. We'll trace its origins from the earliest experiments and curious minds, through decades or even centuries of refinement and innovation, to the sophisticated systems we rely on today. These aren't just stories about machines and inventions, they're stories about human ingenuity, about problems solved one small step at a time, about the persistent belief that we can build something better. Tonight's topic is what makes the internet possible: the internet undersea cables. Over the next few hours, we'll discover a number of fascinating facts about how this technology came to be, the brilliant minds who developed it, and the incremental improvements that brought us from those first tentative experiments to the remarkable capabilities we have today. You don't need to stay awake for all of it. In fact, the whole point is that you won't. Let my voice become background, a gentle companion as you drift toward sleep. If you wake during the night, the story will still be here, continuing its patient exploration through history and innovation. There's no test tomorrow, no need to remember every detail, just relax and let the story wash over you. So close your eyes if you'd like. Breathe deeply, and let's begin our journey into the deep sea. Imagine the internet. You might picture satellites orbiting high above Earth, beaming signals through space. You might think of wireless signals floating invisibly through the air around us. But the truth is far more grounded, far more tangible than most people realize. Deep beneath the ocean's surface, resting on the seafloor in darkness and silence, lies the real backbone of our connected world. Over 99% of all global internet traffic travels through undersea cables. Not satellites, not wireless towers. Cables. Physical, tangible cables that stretch across the ocean floor, connecting continent to continent in an intricate web of fiber optic lines. These cables span an astonishing 1.4 million kilometers across the world's oceans. To put that in perspective, that's enough cable to wrap around the Earth's equator more than 35 times. It's a distance so vast, it's almost impossible to comprehend. And yet, all of it lies hidden beneath the waves, doing the quiet, invisible work of keeping our world connected. Every email you send, every video you stream, every message you share with someone on another continent, nearly all of it passes through these underwater cables at some point in its journey. They form the physical backbone of global connectivity, the infrastructure that makes our modern digital world possible. Without them, international communication as we know it would simply cease to exist. And yet, most of us never think about them. They link continents invisibly, out of sight and out of mind, working tirelessly in the darkness of the deep ocean. It's interesting, isn't it? We live in an age where everything feels wireless, where connection feels like magic happening through the air. Most people naturally assume that satellites run the internet. After all, we hear about satellite internet, satellite communications, GPS satellites. It seems logical that these orbiting machines would be handling the heavy lifting of global data transfer. But satellites, while important for certain applications, actually carry less than 1% of international internet traffic. They're simply too slow and too limited in capacity compared to fiber optic cables. The real work, the enormous task of moving the world's data from place to place, happens through cables. Physical cables, resting on the ocean floor, doing the unglamorous but essential work that keeps our world running. And this system, remarkable as it is also surprisingly fragile. A single cable failure can disrupt entire regions within seconds. Imagine that for a moment. One break in one cable, perhaps caused by a ship's anchor dragging across the seafloor, or an underwater earthquake, or even a curious shark biting into the cable's protective coating. And suddenly, millions of people lose their connection to the outside world. Internet speeds slow to a crawl. Businesses can't process transactions. Communications are severed. Entire countries have experienced internet blackouts because of damage to just one or two critical cables. The system that feels so robust, so ever-present in our lives, can be disrupted by surprisingly simple accidents. What makes the system even more vulnerable is the way these cables are distributed across the ocean floor. They don't spread out evenly, taking different paths across the vast expanses of ocean. Instead, they follow similar routes, converging at what are called chokepoints. These chokepoints concentrate dozens of cables into narrow seabed corridors, bottlenecks where much of the world's internet traffic funnels through relatively small geographic areas. Places like the Strait of Malacca in Southeast Asia, the Suez Canal region, the waters around Singapore. These are digital highways where cables cluster together, passing through narrow passages dictated by geography, politics, and economics. These choke points are efficient, certainly. They reduce the complexity of routing, make maintenance more manageable, and follow the natural paths that ships and trade routes have used for centuries. But they also create single points of failure, places where damage or disruption can have cascading effects across the global internet. It's a reminder that for all our technological advancement, our digital infrastructure is still bound by physical reality, by the constraints of geography and the unpredictability of the natural world. So, as you drift toward sleep tonight, think about those cables. 1.4 million kilometers of fiber optic line, resting in the darkness beneath the waves, carrying the conversations, the ideas, the connections that make up our modern world. They're down there right now, in the cold and the pressure of the deep ocean, doing their quiet, essential work. Invisible, but absolutely vital. The hidden backbone of everything we do online. The dream of instant communication across oceans is older than you might think. Long before the internet, before computers, even before the telephone became common, visionaries imagined a world where messages could travel from continent to continent in moments rather than weeks. And it all began with one ambitious man and one audacious project that would change the world forever. In 1858, an American entrepreneur named Cyrus Field accomplished something that many thought impossible. He laid the first transatlantic telegraph cable, stretching across the vast Atlantic Ocean from Ireland to Newfoundland. Imagine the scene. Ships working in tandem, carefully paying out cable into the depths below, mile after mile of copper wire descending into darkness. It was an engineering marvel, a triumph of human ambition and determination. When that cable was finally connected, when the first message successfully traveled beneath the ocean from one continent to another, it must have felt like magic. The world had suddenly become smaller, but that first cable, despite all the effort and expense, failed after transmitting just one message, one single message, and then silence. The insulation had degraded, seawater had penetrated the cable's protective layers, and the dream collapsed. It would have been easy to give up, to declare the project impossible, too ambitious for the technology of the day. But Cyrus Field didn't give up. He tried again. 8 years later, in 1866, the first successful transatlantic cable began operating reliably. This time, the technology was better, the understanding deeper, the execution more careful. And this time, it worked. Messages began flowing regularly between Europe and North America. traveling in minutes across a distance that had previously taken weeks by ship. The world of global communication had truly begun. The story of how they achieved this success is fascinating in itself. In 1865, during one of the cable-laying attempts, disaster struck. The cable snapped and sank to the ocean floor, leaving the project in ruins. But here's where it gets remarkable. They didn't just abandon that broken cable. A ship called the Great Eastern, the largest vessel in the world at that time, went back out to sea. The crew managed to find the broken cable lying on the ocean floor. Grapple it, haul it back up from the depths, splice it together, and complete the connection. They recovered and repaired a cable from the bottom of the Atlantic Ocean. In 1865, think about that for a moment. The ingenuity, the determination, the sheer audacity of even attempting such a thing. Once that successful cable was operational, the pace of progress accelerated rapidly. By 1870, the Anglo-American cable had cut the time it took to send a telegram from New York to London down to just 5 minutes. 5 minutes, what had once taken 2 weeks by the fastest ship, now took less time than brewing a pot of tea. The impact on business, on diplomacy, on journalism, on human connection itself. It's hard to overstate. The world had fundamentally changed. The British Empire, recognizing the strategic and economic importance of these cables, embarked on an ambitious project called the All Red Line. Completed in 1885, it was a network of copper cables that encircled the entire British Empire, connecting London to Canada, to Australia, to India, to Singapore, creating a communications network that spanned the globe and touched every corner of British influence. All red referred to the red that traditionally marked British territories on maps. This network meant that British officials, merchants, and military commanders could communicate across vast distances within their own secure network, without relying on cables controlled by other nations. But the ambition didn't stop there. In 1903, engineers completed the Pacific Cable, stretching an astonishing 11,000 kilometers across the Pacific Ocean. At the time, it was the world's longest cable, an engineering feat that pushed the boundaries of what was thought possible. Laying cable across the relatively narrow Atlantic was one thing. Spanning the vast expanse of the Pacific, with all its depth and distance and unpredictable conditions, was quite another. And the challenges weren't just technical or logistical. Sometimes they were unexpected. In 1911, a cable ship called the CS Monarch was laying cables in the Pacific when the crew encountered a peculiar problem. Sharks, these curious creatures, attracted perhaps by the electromagnetic fields generated by the cables, or simply investigating this strange new object in their territory, began attacking the cables. They would bite into the protective layers, damaging the insulation and threatening the entire operation. The crew of the Monarch found themselves literally battling sharks while trying to lay cables across the ocean floor. It sounds almost comical now, but at the time it was a serious problem that required real solutions. Engineers eventually developed tougher outer coatings and protective measures to resist these underwater predators. As the decades passed, the technology continued to evolve. In 1924, Western Union laid a cable that used a revolutionary material called permalloy in its construction. This special alloy had remarkable properties that halved signal loss compared to previous cables. Signal loss had always been one of the greatest challenges in undersea cables. The longer the cable, the weaker the signal became as it traveled through the wire, until eventually it degraded into uselessness. Any advancement that reduced this loss was enormously valuable, allowing for longer cables, clearer signals, and more reliable communication. But perhaps the most significant leap came in 1956, with the completion of TAT-1. TAT stood for transatlantic telephone. And this cable represented something fundamentally new. All previous cables had carried telegraph signals, dots and dashes. Simple on and off pulses that could be decoded into letters and words. TAT-1 enabled the first transatlantic telephone calls. For the first time, you could actually hear someone's voice, speaking to you in real time from across the Atlantic Ocean. Not reading their words in a telegram, but hearing them speak, hearing the emotion and nuance in their voice. The technology that made this possible was ingenious. Every 75 kilometers along the length of TAT-1, engineers installed vacuum tube repeaters. These devices, powered by electricity and housed in protective casings, would receive the weakening voice signal, amplify it back to full strength, and send it onward to the next repeater. Like a relay race where each runner passes the baton to a fresh teammate, these repeaters kept the signals strong across thousands of kilometers of ocean floor. It's remarkable to think about those vacuum tubes, sitting in their sealed chambers on the ocean floor, glowing faintly in the absolute darkness of the deep sea, amplifying voices traveling from continent to continent. There was something almost poetic about it. Human voices, carried by electrical impulses through copper wire, kept alive by these glowing tubes, powered by electricity flowing through the same cable, all resting in perfect darkness under immense. TAT-1 could carry 36 telephone conversations simultaneously, 36 by today's standards. That seems impossibly small. A modern fiber optic cable can carry millions of times more data. But in 1956, 36 simultaneous transatlantic phone calls was extraordinary. It was the beginning of the modern era of global communication. From Cyrus Field's failed first attempt in 1858 to the successful telephone cable of 1956 spans nearly a century of innovation, determination, and human ingenuity. Each generation pushed a little further, solved problems their predecessors couldn't, and built upon the foundations laid before them. Those early pioneers, laying copper cables across the ocean floor in wooden ships, fighting sharks and storms and technical limitations, created the networks that would eventually evolve into the internet infrastructure we depend on today. As you settle deeper into sleep, imagine those early cables still resting on the ocean floor, perhaps alongside their modern fiber optic descendants. Silent now, no longer carrying signals, but still there. Physical reminders of the moment when humanity first connected the continents, when the oceans stopped being barriers and became bridges instead. Now that we've explored the history of undersea cables, let's shift our focus to something equally fascinating: how these modern cables actually work. How does data travel thousands of kilometers beneath the ocean? What's happening inside those cables right now, at this very moment, as information flows from continent to continent? The physics and engineering behind it all is remarkably elegant. Modern undersea cables transmit data as light pulses through glass fibers, not electrical signals traveling through copper wire, like those early telegraph cables. Light, pure light, flickering on and off billions of times per second, carrying the ones and zeros that make up all digital information. Each cable contains multiple strands of glass fiber, thinner than a human hair. And through each of these impossibly thin strands, light travels, carrying vast amounts of data across the ocean floor. But how does light stay inside such a thin fiber? Why doesn't it just scatter out into the surrounding ocean? The answer lies in a beautiful principle of physics called total internal reflection. The glass fiber has two parts: a core in the center and a cladding wrapped around it. These are made of slightly different types of glass with different refractive indices. When light tries to escape from the core into the cladding, the difference in refractive index causes it to reflect back into the core, like a ball bouncing off a wall. This happens continuously along the entire length of the fiber. The light bounces back and forth, trapped inside the silica core, traveling forward but unable to escape. It's held in a tunnel of glass, racing through darkness beneath the ocean. And it travels fast, remarkably fast. These signals move at approximately 200,000 kilometers per second underwater. That's about 2/3 the speed of light in a vacuum. To put that in perspective, a signal could travel from New York to London in about 28 milliseconds, less than the blink of an eye. The delay you sometimes notice on international video calls isn't usually the cable itself. It's the processing at either end, the routing through various networks, the conversion from fiber to copper to wireless and back again. The light traveling through these fibers isn't just any light. Engineers use lasers operating at a very specific wavelength, 1550 nanometers. This isn't arbitrary. Glass is transparent, yes, but not perfectly transparent. Different wavelengths of light are absorbed differently as they travel through glass. At 1550 nanometers, glass fiber has its lowest absorption rate. At this wavelength, light can travel further with less loss than at any other wavelength in the spectrum. It's the sweet spot, the perfect frequency for long-distance fiber optic communication. And the signal loss, even at this optimal wavelength, is astonishingly low. Only 0.2 decibels per kilometer. To understand how remarkable that is, consider this. After light travels 1 kilometer through these glass fibers, it retains about 95% of its original intensity. After 10 kilometers, about 80%. Even after 100 kilometers, a measurable signal remains. This efficiency is what makes transoceanic cables possible. If glass absorbed light more readily, the entire system simply wouldn't work. You could look through a window made of this fiber optic glass that's several kilometers thick and still see through to the other side. That's how transparent this material is. But a single fiber carrying a single beam of light, even at incredible speeds, wouldn't be enough to handle the enormous volume of data flowing between continents. Engineers needed a way to increase capacity without laying thousands of separate cables. The solution they developed is called dense wavelength division multiplexing, often abbreviated as DWDM. It's an elegant technique that packs 100 or more separate channels into a single fiber. Here's how it works. Instead of sending just one wavelength of light through the fiber, engineers send many different wavelengths simultaneously. Think of it like colors of the rainbow, each slightly different from the next. Each wavelength acts as a separate channel, carrying its own stream of data, and all of them travel through the same fiber at the same time without interfering with each other. At the receiving end, these wavelengths are separated out and decoded individually. It's like having 100 different conversations happening simultaneously in the same room, each at a different pitch, and being able to hear and understand all of them distinctly. Each of these wavelengths can carry between 40 and 100 gigabits per second. Gigabits, that's billions of bits of data every second on each individual wavelength. And remember, there are 100 or more of these wavelengths traveling together through a single fiber. The total capacity becomes staggering. A single modern undersea cable can transmit more data in 1 second than you could store on thousands of traditional hard drives. To extract every possible bit of information from these light signals, engineers use a technique called coherent detection. This sophisticated method enables phase-sensitive decoding, allowing a single fiber to carry beyond 25 terabits per second. Terabits, 25 trillion bits of information, flowing through a strand of glass thinner than a hair every single second. The mathematics and engineering required to achieve this borders on the miraculous. Coherent detection looks not just at whether the light is on or off. but at the phase of the light wave itself. The subtle timing of the oscillations, it's like the difference between just hearing whether a musical note is playing or not, versus hearing the exact pitch, timbre, and harmonics of that note. The amount of information you can extract increases dramatically, but physics, as elegant as it is, also presents challenges. When light travels through glass at such high intensities over such long distances, strange things start to happen. Nonlinear effects emerge. The light itself begins to change the properties of the glass it's traveling through, which in turn affects the light. Two of the most significant of these effects are called Kerr scattering and Brillouin scattering. Kerr scattering, named after the Scottish physicist John Kerr, who discovered it, occurs when intense light slightly changes the refractive index of the glass. The glass literally becomes more or less transparent, depending on the intensity of light passing through it at that moment. This causes different wavelengths to travel at slightly different speeds, and even causes different parts of the same pulse to travel at different speeds. The carefully timed pulses of light that carry information begin to smear out, to blur together. Brillouin scattering is even more peculiar. It happens when light interacts with acoustic vibrations in the glass itself. Sound waves, essentially, though at frequencies far beyond what human ears could detect. The light bounces off these acoustic waves, and some of it scatters backward, traveling in the opposite direction from the data stream. Energy that should be moving forward, carrying information, instead heads backward, lost and wasted. Both Kerr and Brillouin scattering distort the signal, mixing up the carefully orchestrated light pulses, threatening to turn meaningful data into noise. These nonlinear effects become more pronounced the longer the cable, the more intense the light, and the higher the data rates. And since engineers are constantly pushing for longer cables, brighter signals, and higher capacities, these effects are always lurking, waiting to cause problems. Managing them, compensating for them, working around them. This is one of the central challenges in modern fiber optic engineering. As you relax and let these thoughts wash over you, picture the light right now, racing through fibers beneath the ocean. 100 different colors, each one flickering billions of times per second. Each one carrying conversations and videos and messages and data. All of it traveling at 200,000 kilometers per second, bouncing infinitely down tunnels of impossibly pure glass, working against the subtle but persistent distortions that physics imposes. It's happening right now, in the cold darkness, reliably and ceaselessly, connecting our world. So we've seen how nonlinear effects like Kerr and Brillouin scattering threaten to distort the signals traveling through undersea cables. But engineers don't simply accept these limitations. They've developed remarkable techniques to counteract these problems, to work with the physics rather than against it, finding elegant solutions that allow light to travel thousands of kilometers and still arrive intact. One of the fundamental approaches involves counteracting dispersion with tailored refractive indices. Remember, dispersion is the tendency for different wavelengths of light, or different parts of a light pulse, to travel at different speeds through the fiber. Left unchecked, this would cause the sharp, distinct pulses that represent data to spread out and blur together. But by carefully controlling the exact composition and structure of the glass fiber during manufacturing, engineers can design fibers whose properties naturally compensate for dispersion. It's a bit like designing a racetrack where different lanes have different surfaces, carefully calibrated so that faster cars get slightly rougher pavement while slower cars get smoother surfaces. All working out so that everyone crosses the finish line at the same time. The refractive index profile of the fiber, the way it changes from the center core outward to the cladding, can be precisely tailored to make different wavelengths naturally travel at compensating speeds. What physics tries to pull apart, clever engineering brings back together. But there's another, more subtle form of dispersion that engineers must contend with. It's called polarization mode dispersion. Light waves oscillate, and the direction of that oscillation is called polarization. In a theoretically perfect fiber, all polarizations would travel at exactly the same speed. But real fibers have tiny imperfections, microscopic stress points, gentle bends, variations in the glass structure. These cause different polarizations to travel at slightly different speeds. Over a few kilometers, this difference is negligible. But over thousands of kilometers, these tiny differences accumulate. The light pulses, which started out sharp and well-defined, arrive at their destination smeared out, with different polarizations arriving at slightly different times. It's like listening to an orchestra where all the musicians are playing the same piece, but some are running a fraction of a second behind the others. The music becomes muddy, indistinct. The solution is remarkable. Polarization mode dispersion is corrected dynamically in real time. Electronic circuits at the receiving end constantly analyze the incoming signal, detecting the distortion caused by polarization effects. Then, using sophisticated digital signal processing, they mathematically reconstruct what the original signal must have been. This happens continuously, automatically, billions of times per second, adapting to changing conditions in the fiber. The cable might shift slightly on the ocean floor, temperature might change, pressure might vary, and the correction algorithms adapt instantly, maintaining signal quality no matter what. Perhaps the most elegant solution to the challenge of long-distance fiber transmission comes from exploiting a phenomenon called solitons. A soliton is a special kind of wave that maintains its shape as it travels. In most systems, waves tend to spread out, to dissipate their energy and lose their form. But solitons are different. They're stable, self-reinforcing. In fiber optics, engineers can create light pulses that are soliton pulses, carefully designed to balance dispersion and nonlinearity over vast distances. Here's the beautiful part. Remember how dispersion tries to spread the pulse out, while nonlinear effects like Kerr scattering can compress and distort the pulse. These seem like two separate problems, but in a solitone, they become the solution. The pulse is shaped precisely so that dispersion and nonlinearity oppose each other, cancelling out in a delicate balance. Dispersion tries to spread the pulse. Nonlinearity tries to compress it, and they fight to a draw, leaving the pulse unchanged, traveling kilometer after kilometer after kilometer without degrading. It's like a surfer riding a wave, finding that perfect position where gravity pulling them down and the wave pushing them up create a stable equilibrium, allowing them to ride seemingly forever. The solitone pulse rides the physics of the fiber, balanced between opposing forces, stable and preserved across the vast distances of the ocean. Even with all these sophisticated techniques for preserving signal quality, light cannot travel forever through fiber without eventually weakening. The 0.2 decibels per kilometer of loss is small, but it's not zero. After enough distance, even with the most perfect glass and the most carefully chosen wavelength, the signal fades. This is where amplification becomes necessary. One particularly clever technique is called Raman amplification. This method uses the fiber itself as the amplifying medium. Powerful pump lasers shine light into the fiber at specific wavelengths, and through a process called stimulated Raman scattering, energy is transferred from those pump lasers to the weakening data signals. The data signals are boosted back up to full strength, all while still traveling through the fiber, with no need for separate amplification devices. This extends repeater spacing to 150 kilometers or more between amplification points. Fewer repeaters mean fewer potential failure points. simpler systems, lower costs. But the primary technology used in undersea cable repeaters is based on erbium-doped fiber amplifiers. These are special sections of fiber that have been infused with atoms of erbium, a rare earth element with remarkable optical properties. When pump light at the right wavelength is introduced, it excites those erbium atoms to a higher energy state. As the data signals pass through, those excited erbium atoms release their energy, amplifying the signals. It's a purely optical process. Light goes in, brighter light comes out, with no conversion to electrical signals and back. This makes the process incredibly efficient and reliable. These repeaters, whether using Raman amplification or erbium-doped fiber, need power. They're sitting on the ocean floor, miles from any electrical outlet, in complete darkness under crushing pressure. How do they receive the energy they need? The answer is both simple and ingenious. The cable itself carries electricity. Running alongside the optical fibers are copper conductors. And through these conductors, power stations at either end of the cable send electrical current. The voltages involved are enormous. Repeaters are powered at 3,000 to 12,000 volts. Why such high voltages? Because of basic electrical physics. For a given amount of power, higher voltage means lower current. And lower current means less energy is wasted as heat in those long copper conductors. It's far more efficient to send power at 12,000 volts over thousands of kilometers than at lower voltages. At each repeater along the cable's length, this high-voltage current is tapped off and converted to the levels needed to operate the amplification equipment. The erbium atoms get pumped, the signals get amplified, and the data continues its journey. So that's the complete picture. Light enters the cable, carefully tuned to 1550 nanometers. It's split into 100 or more wavelengths through dense wavelength division multiplexing. Each wavelength carries tens or hundreds of gigabits per second, flickering billions of times per second with the ones and zeros of digital data. The fiber itself is engineered with tailored refractive indices to counteract dispersion. Sophisticated electronics at the receiving end correct for polarization mode, dispersion in real time. Solitone pulses balance nonlinear effects against dispersion to maintain their shape. Every 150 kilometers or so, Raman amplification or erbium-doped fiber amplifiers boost the signal back to full strength. Powered by thousands of volts flowing through copper conductors embedded in the cable. And through this intricate dance of physics and engineering, data flows reliably and ceaselessly across the ocean floor. As you drift toward sleep, let your mind rest on the elegance of it all. Problems turned into solutions. Physics harnessed rather than fought against. Light and glass and rare earth elements and electric current, all working together in the darkness beneath the waves, carrying the world's conversations and connections, pulse after pulse, wavelength after wavelength, without pause, without rest. We've explored how data travels through undersea cables as pulses of light. But before any of that can happen, before a single bit of information crosses the ocean, someone has to manufacture these remarkable cables. And the process of creating something that can survive on the ocean floor for decades is an engineering achievement in itself. Let's follow the journey from raw materials to finished cable, from factory floor to ocean abyss. It all begins with silica, pure silicon dioxide, the same material that makes up sand and quartz, but refined to extraordinary purity. To create the optical fiber, engineers start with something called a silica preform. This is a thick rod of ultra-pure glass, and creating it requires extreme precision and extreme temperatures. The preforms are grown at 2200 degrees Celsius. Hot enough to melt most metals, hot enough to glow brilliant white. At these temperatures, gases containing silicon and oxygen react and deposit layer upon layer of pure silica, building up the preform slowly, carefully, molecule by molecule. Each preform, despite being relatively small, yields an astonishing amount of fiber. A single preform can be drawn into 1,000 kilometers of optical fiber. 1,000 kilometers from one rod of glass. Think about that transformation for a moment. Something you could hold in your hands becomes a thread stretching across a continent. But it's not just pure silica. The process uses something called modified chemical vapor deposition to build hundreds of doped layers into the preform. Different layers are infused with tiny amounts of other elements, germanium or fluorine, carefully controlled to create the precise refractive index profile needed for total internal reflection. The core, where light will travel, has one refractive index. The cladding around it has another, and between them might be dozens of additional layers, each with its own carefully calculated optical properties, all working together to trap and guide light with minimal loss. Once the preform is complete, comes one of the most delicate steps in the entire manufacturing process. The preform is heated until the glass becomes soft and pliable, and then it's stretched. Drawn out like taffy, the thick rod of glass becomes thinner and thinner, pulled by precise mechanical systems that maintain constant tension and temperature. The result is a fiber just 50 microns in diameter, 50 millionths of a meter, thinner than a human hair, thinner than most of the dust particles floating in the air around you right now. And yet, this impossibly thin strand of glass is also incredibly strong. The drawing process aligns the molecular structure of the glass, creating a fiber that can withstand remarkable tension without breaking. But it's also fragile in other ways. A tiny scratch, a microscopic imperfection on the surface, and the fiber can fail. So, immediately after drawing, the fiber is coated with protective layers of polymer, sealed away from the environment before anything can damage it. But a bare optical fiber, even coated, is nowhere near strong enough to survive the ocean. The next step is bundling multiple fibers together and combining them with structural support. Stranding machines twist the fibers around a central steel wire. These machines spin at up to 1,000 rotations per minute, weaving the delicate glass fibers around the strong steel core in a carefully controlled helix. The king wire provides tensile strength, allowing the cable to be pulled and handled during installation without stressing the optical fibers themselves. Then comes layer after layer of protection. First, polyethylene sheaths are extruded directly onto the cable. The polyethylene is heated to 200 degrees Celsius and forced through dies at 20 bar of pressure, creating a seamless waterproof barrier around the fiber bundle. This sheath must be perfect, with no gaps, no bubbles, no weak points where water could eventually penetrate. Even at the crushing pressures of the deep ocean, even over decades of exposure, this polymer barrier must remain intact. For cables that will rest in shallower waters, where the risk of damage is higher, additional armor is added. Steel wire is wound around the cable, sometimes in multiple layers, creating a protective barrier that can withstand crushing and abrasion. Fishing trawlers dragging nets across the bottom, ship anchors being dropped and dragged, undersea landslides, curious marine life, all of these threats exist in the shallower continental shelf waters where cables first leave shore. The steel armor protects against all of them. For cables destined for the very deepest parts of the ocean, different protection is needed. The pressure at those depths is extraordinary. We're talking about 1,500 bar of pressure. That's 1,500 times atmospheric pressure, or about 22,000 pounds per square inch. At those pressures, water will force its way through the tiniest opening, the smallest imperfection, so cables for the deep ocean are protected by seam-welded steel tubes. The steel is rolled into a tube around the cable, and then the seam is welded shut with laser precision, creating a completely sealed environment that can survive 1500 bar of pressure without allowing a single molecule of water inside. Before any cable leaves the factory, it undergoes rigorous testing. Each section is tensile tested, subjected to forces up to 70,000 newtons. That's the equivalent of hanging 7 metric tons from the cable. If there's any weakness, any flaw in the construction, the testing will reveal it. Better to discover a problem in the factory than in the middle of the ocean during installation, or worse, years later when the cable is already in service. Every meter of finished cable is also examined with X-rays, looking for microscopic defects that might not be visible to the naked eye. Is there a tiny void in the polyethylene sheath? Is there a stress point in one of the steel armor wires? Is there any irregularity in the fiber bundle itself? The X-ray inspection catches these problems before the cable ever leaves the manufacturing facility. The result of all this engineering and precision is a cable that can survive on the seabed for 25 years or more. 25 years of constant use, of light pulses racing through at billions of cycles per second, of pressure and cold and slow chemical processes, of tiny sea creatures settling on its surface, of sediment slowly covering it. Through all of this, the cable continues working, continues transmitting, continues connecting continents with the same reliability as the day it was installed. Think about what that means. A cable installed today might still be carrying data in the 2050s. It will outlast multiple generations of the computers and smartphones at either end. It will carry technologies and applications that haven't even been invented yet. The cable doesn't care what information flows through it. It simply does its job, year after year, pulse after pulse, in the eternal darkness of the ocean floor. The manufacturing process, from silica dust to finished cable, can take months for a single transoceanic system. Thousands of kilometers of fiber must be drawn, tested, bundled, armored, and spooled. Quality control happens at every stage because there's no room for error. Once the cable is on the ocean floor, repairs are difficult and expensive. The cable must work, must last, must continue functioning reliably for decades. There's something almost meditative about the precision required. Every measurement exact, every temperature controlled, every process verified and documented. The workers who build these cables are creating something that will outlive them, infrastructure that will serve humanity for generations. In an age of disposable technology, of devices that become obsolete in years or even months, there is something profound about creating something designed to last a quarter century in one of the harshest environments on Earth. As you settle deeper into rest, imagine the factories where these cables are made, the glow of the furnaces where silica preforms are grown at impossible temperatures, the steady rhythm of the stranding machines, spinning at 1,000 rotations per minute, weaving glass and steel into a single unified structure, the careful hands guiding polymer extrusion, the focused eyes examining X-ray images for flaws, and the finished product kilometers upon kilometers of cable precisely engineered rigorously, tested, ready to be loaded onto ships and carried out to sea, ready to be laid on the ocean floor where it will work quietly and reliably for decades to come. We've explored how cables are manufactured, how they work, the physics that governs them. But before any data can flow, before those light pulses can begin their journey, someone has to actually lay the cable on the ocean floor. And this process, this ballet of engineering performed at sea, is a remarkable achievement in its own right. The journey begins with specialized cable ships. These aren't ordinary vessels. They're purpose-built for one of the most demanding tasks in maritime engineering. In their holds, they carry massive circular tanks, carefully climate-controlled, and into these tanks are coiled thousands of kilometers of cable. A single cable ship can carry up to 5,000 tons of cable in these giant tanks. 5,000 tons. That's the weight of more than 30 blue whales, all coiled carefully, layer upon layer, waiting to be paid out across the ocean floor. The cable must be loaded with extraordinary care. Any kinks, any sharp bends, any stress points created during loading could become failure points once the cable is deployed. So the coiling happens slowly, methodically, with constant monitoring of tension and curvature. It can take weeks just to load a cable ship for a major transoceanic installation. Once at sea, once the ship reaches the point where the cable laying will begin, the real work starts. The cable is fed out from the tanks, through a series of tensioning devices and guides, and over the stern of the ship into the water. The payout speeds can reach 10 to 12 kilometers per hour. The ship moves forward steadily. The cable unspools behind it, descending through the water column towards the ocean floor far below. 10 to 12 kilometers per hour might not sound particularly fast. You could walk that speed, almost, but consider what's happening. Thousands of tons of cable, each meter of which cost thousands of dollars to manufacture, is being precisely laid along a route that might be 5,000 or 6,000 meters below the surface, in total darkness, often in areas never before visited by humans. And this must be done with precision. The cable must follow the planned route, must avoid obstacles, must be laid with the right amount of slack to account for seafloor topography. This is where technology becomes crucial. GPS and inertial navigation systems work together to compensate for currents and waves. The ship is constantly being pushed by wind and current, constantly rising and falling with the swells. But the cable route was planned to within meters, carefully surveyed to avoid hazards, optimized for the smoothest possible path. The navigation systems must keep the ship on track despite all these forces trying to push it off course. The inertial navigation system tracks every tiny movement of the ship, every pitch and roll, every yaw and heave, combined with GPS positioning, which gives absolute location. The ship's computers can calculate exactly where the cable is being laid at any given moment, compensating for how the cable arcs through the water column, how currents at different depths might push it, how the ship's motion affects the payout point. It's a three-dimensional problem solved in real time, constantly, for days or weeks at a time. In shallower waters, near the continental shelves where the risk of damage is highest, the cable isn't simply laid on the surface of the seabed. Instead, it must be buried for protection. This is where cable plows come in. These remarkable machines are lowered to the seafloor and dragged behind the cable ship. As they move across the bottom, they cut trenches into the seabed, 2 meters deep, and the cable is guided into these trenches as they're created. A 2-meter deep trench might not sound like much, but consider the environment. The seafloor isn't smooth, empty sand. There are rocks, there's consolidated sediment, there are often layers of clay and gravel. The plow must cut through all of this, and do so without damaging the cable, without getting stuck, without deviating from the planned route. The forces involved are immense, and the process is slow. Burial progresses at only 0.2 kilometers per hour. That's 200 meters per hour, slower than most people walk. At that rate, burying just 1 kilometer of cable takes 5 hours. For a cable system that might have hundreds of kilometers in shallow water that requires burial, this part of the installation can take weeks. The cable ship must maintain perfect position and speed during all of this. Too fast, and the plow can't keep up. The cable doesn't get buried properly. Too slow, and too much slack pays out. The cable lies in loops on the seafloor, creating potential snag points and stress concentrations. The crew must monitor dozens of parameters constantly: tension on the cable, depth of the plow, speed over ground versus speed through water, weather conditions, equipment status. It requires constant attention, constant adjustment. Not all cables are simple point-to-point connections, though many modern cable systems include branch cables that pre-connect islands or smaller coastal nations to the main trunk. These branching units are remarkable pieces of engineering in themselves. They're underwater junction boxes where multiple cables meet, where signals can be routed in different directions. Some branch cables extend up to 500 kilometers from the main trunk to reach remote islands. Installing these requires even more precision, because now you're not just laying one cable, you're laying multiple cables that must meet at exact predetermined points on the ocean floor. The installation process must also respect the natural world. Under International Cable Protection Committee rules, laying operations halt during whale migrations. These massive marine mammals use many of the same ocean corridors that cables follow, and the noise and activity of cable installation could disturb them during critical migration periods. So the ships wait, the crews pause their work, and the whales pass by undisturbed. It's a reminder that even in our most ambitious engineering projects, we share this planet with other species, and we have a responsibility to minimize our impact. The ocean floor is not static. Sand dunes underwater, called sand waves, migrate over time, pushed by currents and storms. Before a cable is laid, sonar surveys map the seafloor in detail, noting the positions and heights of these sand waves. And after the cable is installed, surveys track sandwave migration yearly. If a sand wave is moving toward a buried cable, threatening to expose it or create stress points, action can be taken. Additional burial might be needed, or protective mattresses placed over vulnerable sections. Despite all the planning and effort, not all cable can be buried. About 15% of cables remain unburied due to rocky seabed. In areas where the seafloor is solid rock, or where coral formations exist, or where the substrate is too hard for plows to penetrate, the cable must simply be laid on the surface. These sections are carefully routed to avoid known hazards, and the cable is often weighted or secured to prevent it from moving. But they remain vulnerable, protected only by their armor and by the remoteness of their location. And even after successful installation, the ocean continues to shape the cable's fate. Deep-sea cables slowly drift laterally over time. The seafloor itself moves, pushed by tectonic forces, by underwater landslides, by the slow accumulation of sediment. Currents can gradually push exposed sections of cable sideways. Over years and decades, the cable's position can shift by meters or even tens of meters from where it was originally laid. This movement must be accounted for in the cable's design. There must be enough slack, enough flexibility to accommodate this slow drift without creating dangerous tension. The entire process of laying a transoceanic cable system can take months. Multiple cable ships might work simultaneously on different sections. Coordination must be precise. The cable manufactured months ago must match exactly with cable being laid today. Splice points must line up. Timing must account for weather windows, equipment availability, permit restrictions, and 100 other factors. And through it all, the crew works in one of the most demanding environments imaginable. Miles from shore, in all weather conditions, handling equipment worth millions of dollars, knowing that a single mistake could delay the project by weeks and cost enormous sums. It requires skill, experience, patience, and an almost meditative focus on the task at hand. As you rest now, imagine those cable ships somewhere out on the ocean at this very moment. The steady hum of engines, the rhythmic payout of cable over the stern, the constant attention of the crew monitoring their instruments. Below them, kilometers down, a cable settles onto the seafloor, beginning its decades-long service connecting our world. It's happening right now, somewhere. The slow, patient work of building the infrastructure that makes our connected world possible. For all their careful engineering, for all the sophisticated manufacturing and precise installation, undersea cables are not indestructible. They break, they fail, and when they do, the consequences can be significant. Let's talk about what happens when things go wrong beneath the ocean. Cables break between 100 and 200 times every year, globally. That's a cable failure happening somewhere in the world every few days. Think about that for a moment. With all the protection, all the armor, all the careful routing and burial, failures still happen with surprising regularity. Some are minor, causing temporary slowdowns as traffic reroutes through other cables. Others are catastrophic, severing entire regions from the global internet until repairs can be made. And these breaks aren't evenly distributed across the ocean floor. The vast majority happen in one particular zone. 70% of all cable faults occur in shallow waters. In that transition zone between shore and the deep ocean, where the continental shelf gives way to the abyss. This is where cables are most vulnerable, where human activity is most concentrated, where the forces that can damage a cable are most prevalent. The causes of these failures tell a story about how we use the ocean. Anchors cause approximately 40% of all cable breaks. Ship anchors, dragged across the seafloor either deliberately or because the ship is drifting, catch on cables and tear them apart. Sometimes it's accidental. A ship's crew doesn't know a cable is there, despite the charts that mark their locations. Sometimes it's negligence. A captain anchors in a prohibited area or drags anchor while underway. The forces involved are immense. A large ship's anchor can weigh several tons, and when it's being dragged by a vessel that itself weighs thousands of tons, it can tear through cable armor like it's not even there. Fishing causes approximately 25% of breaks. Trawling nets, dragged along the seafloor to catch bottom-dwelling fish, snag cables and pull them up, stressing them beyond their design limits. The heavy doors that hold trawl nets open can run directly over cables, crushing them. Even long lines, with their weighted hooks, can catch on cables and cause damage. And it's not always the fishing industry's fault. Cables sometimes aren't buried as deeply as planned, or sand waves have migrated, exposing previously buried sections. But human activity isn't the only threat. The Earth itself can destroy cables. Earthquakes, landslides, and underwater volcanoes cause deep-sea failures that are often more severe than shallow water breaks. When an earthquake strikes beneath the ocean, it doesn't just shake the water above. It can trigger massive underwater landslides, avalanches of sediment that can bury, crush, or sever cables. These landslides, called turbidity currents when they're particularly large, can flow down submarine canyons at speeds exceeding 100 kilometers per hour, carrying rocks and sediment that scour everything in their path. One of the most dramatic examples of natural cable damage occurred recently. The 2022 Tonga eruption, one of the most powerful volcanic explosions in recent history, didn't just create a mushroom cloud visible from space and send tsunamis across the Pacific. It also buried cables under 100 meters of volcanic ash and debris. 100 meters? That's a 10-story building's worth of material dropped onto the cables. The cables in the immediate vicinity were simply gone, obliterated by the force of the eruption, or buried so deeply that recovery was impossible. Tonga, a nation of over 100,000 people, was cut off from the world. No internet, no international phone calls, no way to communicate with the outside world except by satellite phone or radio. It took weeks to restore even partial connectivity. When a cable breaks, detecting the failure is usually straightforward. The light stops reaching the other end, or the signal quality degrades suddenly. More sophisticated systems can actually measure the exact distance to the break by timing how long it takes for light pulses to reflect back from the failure point. But detecting the problem is the easy part. Fixing it is far more challenging. Repairs are handled by only about 60 specialized ships worldwide. 60 ships to maintain all the undersea cables in all the world's oceans. These vessels are expensive to operate and maintain, and they're not evenly distributed. Some regions have several nearby, ready to respond quickly. Other regions, particularly in the southern hemisphere and remote areas of the Pacific, might be days or even weeks away from the nearest cable repair ship. When a repair ship reaches the site of a break, the first challenge is recovering the cable from the seafloor. This is done using grapnels, large hooks that weigh 6 to 10 tons. These grapnels are lowered on heavy cables, dragged across the seafloor until they snag the broken cable, and then hauled back up. Sounds simple, perhaps, but consider the environment. The water might be kilometers deep. Visibility is zero in those depths. The broken cable might be buried under sediment or covered by marine growth. The grapnel must be precisely positioned, the dragging carefully controlled, and the recovery done with enough force to lift the cable but not so much force that it damages the cable further. Often, the cable must be cut into sections to be recovered. The repair ship grapples one end, brings it to the surface, cuts it, and secures it. Then they move to the other side of the break, grapple that end, bring it up, and cut it. Now they have two ends of cable, both brought to the surface, but with a gap between them where the damaged section was removed. That gap must be filled with new cable, spliced to both of the recovered ends. The entire repair process takes 10 to 20 days per incident. 10 to 20 days. During that time, the ship must maintain position, often in difficult sea conditions. The crew works around the clock when weather permits, knowing that every hour of delay is another hour that internet traffic must route around the damaged cable, causing slowdowns and congestion. The actual joining of the cables is done through a process called fusion splicing, and it requires incredible precision. The fiber optic strands, remember, are only 50 microns in diameter. They must be aligned perfectly, their ends cleaved to create atomically smooth surfaces, and then they're literally melted together using an electric arc. This fusion splicing is done under microscopes in nitrogen tents. The nitrogen creates a clean environment, preventing any contamination that could weaken the splice. Even a single dust particle, a single fiber of cloth, could ruin the splice. The technician doing this work is operating under pressure in every sense. The ship is rolling with the waves, though sophisticated stabilization systems minimize this. Time is critical. The equipment is expensive and delicate, and the splice must be perfect. If it fails, once the cable is back on the ocean floor, the entire repair must be done again. So the technician works carefully, methodically, checking and rechecking each step. Align the fibers, verify the alignment under the microscope, cleave the ends, verify they're smooth and perpendicular, position them in the fusion splicer, initiate the arc, verify the splice strength and optical quality, then repeat for the next fiber in the bundle. Once all the optical fibers are spliced, the entire joint must be protected. It's enclosed in a splice housing, sealed against water pressure and the structural elements of the cable. The steel wire, the copper power conductors, the polymer sheaths, must all be rejoined and protected. The finished splice housing might be a meter or more in length, a bulge in the otherwise uniform cable that contains all these critical connections. And then the cable is paid back out, lowered once again to the ocean floor, laid carefully along the route where the damaged section was removed. The ship moves along the repair path, releasing cable, until finally the two splice points are back on the seafloor and the cable is continuous once again. Tests are run, signals are sent, and if everything works correctly, the cable is back in service. The cost of all this is substantial. Repairs cost $500,000 to $1 million each. That's for a single repair. Ship time, crew salaries, replacement cable, equipment, fuel, it all adds up. For a cable system that breaks multiple times over its lifetime, the repair costs can rival the original installation costs. And that's assuming the repairs go smoothly. If weather delays the work, if the break is in an especially difficult location, if multiple attempts are needed to recover the cable, costs can escalate quickly. Insurance helps cover these expenses, but the real cost isn't just financial. It's measured in disrupted communications, in slower internet speeds, in businesses that can't operate normally, in people who can't connect with loved ones across the ocean. A single cable break in the right location can affect millions of people. And so the cable repair ships stand ready, maintained and equipped, their crews trained and experienced, waiting for the inevitable call that somewhere, somehow, a cable has failed and needs to be restored. It's an unglamorous job, performed far from shore, in difficult conditions, but it's absolutely essential. These repair crews are the emergency responders of the digital age, working in the darkness of the deep ocean to keep our connected world functioning. As you drift toward sleep, spare a thought for those repair ships, somewhere out on the ocean tonight. Perhaps one is working right now, its crew focused on their instruments, carefully manipulating a grapnel kilometers below, searching for a broken cable that needs to be brought back to the surface and made whole again. The work continues, day and night, in calm seas and storms, maintaining the infrastructure we all depend on, but rarely think about. We've talked about how cables are built, how they're laid, how they break and get repaired. But now, let's zoom out and look at the bigger picture. Because while undersea cables span the globe, they don't spread out evenly across the ocean floor. Instead, they converge at specific locations, narrow passages where geography forces them together. These are the choke points of the global internet, and they represent some of the most vulnerable spots in our entire communications infrastructure. Consider the Luzon Strait, that narrow passage of water between Taiwan and the Philippines. It doesn't look particularly special on a map. Just water, like any other stretch of ocean. But beneath the surface, something extraordinary is happening. The Luzon Strait carries up to 80% of all data traffic between Asia and the United States. 80%, most of the communication between the world's largest economy and its fastest growing economic region flows through this one relatively small area of seafloor. Why? Because geography leaves few alternatives. Cables connecting Asia to North America must cross the Pacific, and the most direct, most economical routes happen to funnel through the Luzon Strait. It's the natural path, the shortest distance, the most efficient route, but this efficiency creates vulnerability. An earthquake in the wrong place, an underwater landslide, deliberate sabotage. Any of these could sever multiple cables simultaneously, causing massive disruption to trans-Pacific communications. Or consider the Strait of Malacca, that narrow waterway between Malaysia and Indonesia. It's one of the busiest shipping lanes in the world, with thousands of vessels passing through every year. And beneath those ships, squeezed into a passage just 2.8 kilometers wide at its narrowest point, run over 80 undersea cables. 80 cables, all in close proximity, all vulnerable to the same threats. A ship anchor dragging across the bottom here could potentially damage multiple cables at once. The concentration is staggering. Moving west, we find the Red Sea and the Strait of Bab el-Mandeb at its southern end. This waterway, connecting the Mediterranean via the Suez Canal to the Indian Ocean, routes approximately 10% of global data traffic. It's a geopolitically sensitive region, subject to political tensions, territorial disputes, and occasional conflict. Yet, our global communications depend on cables running through it. The Red Sea also happens to be seismically active, with undersea volcanoes and rift zones where the African and Arabian tectonic plates are slowly pulling apart. Every earthquake in the region poses a potential threat to those cables. Closer to Europe, the Dover Strait between England and France carries about 25% of Europe's data, 25%, through one of the world's busiest shipping channels. Thousands of ships pass through the Dover Strait every week, some of the highest maritime traffic density anywhere on Earth. Each ship represents a potential threat to the cables below. And yet the cables must be there, because Dover represents the shortest, most direct connection between Britain and continental Europe. The Bosphorus, that narrow waterway connecting the Black Sea to the Mediterranean through Istanbul, carries approximately 30% of all data traffic between Europe and the Middle East. It's not just a strategic waterway for shipping and naval vessels. It's a digital highway carrying vast amounts of information. The strait is narrow, the currents are strong, and the seafloor is complex. Laying and maintaining cables here presents unique challenges, yet the geographic necessity is undeniable. Some choke points emerge not from narrow waterways, but from strategic geographic locations that naturally become hubs. Djibouti, a small nation on the Horn of Africa, hosts over 20 cable landings. 20 separate cable systems make landfall in this one country. Why? Because Djibouti sits at the junction between the Red Sea and the Indian Ocean, at the crossroads of cables connecting Europe, Africa, the Middle East, and Asia. It's become a critical nexus in the global cable network, a place where multiple systems interconnect and where data can be routed between different cables and different destinations. The Korea Strait, the body of water between Japan and South Korea, represents another critical link. It connects two of Asia's most technologically advanced nations, to economies deeply integrated into global digital networks. Multiple cables cross this strait, carrying enormous volumes of data. The seafloor here is relatively shallow, making the cables vulnerable to fishing activity and anchor damage. Yet the cables are essential for maintaining the connectivity both nations depend on. Some choke points face unique natural threats. The Sunda Strait, between Java and Sumatra in Indonesia, is home to Krakatau, one of the world's most famous and dangerous volcanoes. Krakatau's 1883 eruption was one of the most violent volcanic events in recorded history, heard thousands of kilometers away, generating tsunamis that killed tens of thousands of people. And Krakatau remains active today. Cables passing through the Sunda Strait face volcanic risk that cables in most other locations simply do. Encounter an eruption, an underwater landslide triggered by volcanic activity, or even significant volcanic sediment flows could damage or destroy cables in this area. And then there's the Drake Passage, that infamous stretch of water between South America and Antarctica. The Drake Passage is renowned among sailors as one of the most challenging bodies of water anywhere on Earth. Storms here can generate waves over 30 meters high. The Antarctic Circumpolar Current, the world's largest ocean current, flows unimpeded around Antarctica, and in the Drake Passage, where it's forced into a relatively narrow gap, it creates some of the most extreme sea conditions imaginable. Few cables cross the Drake Passage because there's simply not much demand for direct connections to Antarctica, but those that do exist, primarily serving scientific research stations, must be built to withstand battering from extreme seas unlike anywhere else. The cables must be heavily armored, secured against movement, designed to survive forces that would destroy cables in calmer waters. What all these choke points have in common is that they represent strategic weak spots in the global internet infrastructure. They're places where the failure of one or two cables could have disproportionate impacts, where geographic necessity has concentrated critical infrastructure, where natural hazards or human activities pose ongoing threats. They're the Achilles heels of our connected world. And it's not just about accidents or natural disasters. These choke points are also strategic targets. Nations that want to disrupt communications, whether for military purposes or cyber warfare or political coercion, know where the cables are concentrated. A submarine with cutting equipment, a naval mine placed precisely, even divers with explosives in shallower areas. These choke points are vulnerable in ways that cables in the open ocean simply aren't. The international community recognizes this vulnerability. There are treaties and conventions aimed at protecting undersea cables, making it illegal under international law to deliberately damage them. Cable locations are charted and published so that ships and fishing vessels can avoid them. Naval forces sometimes patrol critical but ultimately, these thin lines of fiber and steel on the ocean floor remain vulnerable, and the concentration of cables at choke points magnifies that vulnerability. Engineers and cable operators are aware of these risks. Of course, they build redundancy into the system. Multiple cables following slightly different routes, so that the failure of one doesn't bring down the entire connection. They monitor cable health constantly, detecting problems before they become failures when possible. They maintain repair ships and equipment near critical choke points so that response times can be minimized when breaks do occur. But redundancy has its limits. In some choke points, geography simply doesn't allow for much route diversity. The cables must pass through essentially the same area because there's no viable alternative. And while having multiple cables provides backup, a catastrophic event, a major earthquake, a volcanic eruption, a deliberate coordinated attack, could potentially damage multiple cables simultaneously. The more dependent we become on digital connectivity, the more critical these choke points become. As more of our economy moves online, as more critical infrastructure becomes networked, as more of our daily lives depend on internet access, the strategic importance of these narrow passages on the ocean floor grows. They're not just carrying email and web pages anymore. They're carrying financial transactions, control signals for power grids, medical data, industrial operations, government communications. The stakes are higher than ever. As you relax into sleep, picture a map of the world in your mind. Now imagine bright lines representing undersea cables, connecting continents, spanning oceans. Watch as those lines converge at certain points, concentrating at narrow straits and strategic locations, creating dense clusters of cables passing through single vulnerable zones. These are the choke points, the critical junctions where our global connectivity is most concentrated and most at risk. They exist right now on the ocean floor, quietly carrying the world's data through some of the most challenging and vulnerable locations on Earth. We've been talking about cables in terms of engineering, physics, geography, but there's another dimension to these undersea connections, one that's darker and more troubling. Cables aren't just infrastructure, they're strategic assets, they're targets, they're tools of war and espionage. Let's explore the shadow side of undersea cables, the The story begins with the First World War. Within hours of Britain declaring war on Germany in 1914, British naval vessels were already cutting Germany's undersea telegraph cables. It was one of the very first acts of the war, carried out before major troop movements, before the famous battles that would define the conflict. Britain understood something fundamental, that controlling communications meant controlling information, and controlling information was a form of power. By severing Germany's cables, Britain forced German international communications to route through neutral countries or through wireless radio, both of which Britain could intercept and monitor. Germany found itself isolated, unable to communicate securely with its colonies, its embassies, its agents abroad. Every message had to be sent in ways that Britain could potentially read. This information advantage proved invaluable throughout the war. The Second World War saw similar tactics, but more sophisticated. The Allies cut 12 German undersea cables specifically to isolate U-boats, those submarines that prowled the Atlantic hunting merchant convoys. The U-boats relied on shore communications for orders, for intelligence about convoy movements, for coordination. By cutting the cables and forcing Germany to use radio communications that could be intercepted and decrypted, the Allies gained crucial intelligence that helped turn the tide of the Battle of the Atlantic. But cutting cables is the blunt instrument. During the Cold War, intelligence agencies developed far more subtle approaches. One of the most audacious was Project Ivy Bells, a US operation that involved sending submarines deep into Soviet territorial waters to tap undersea cables. Think about the technical challenges involved. Locating the cable on the seafloor in complete darkness, attaching a recording device to it without cutting it, without alerting the Soviets that anything was wrong. The device had to be powered, had to record communications, and had to be periodically recovered and replaced so the recordings could be retrieved. American submarines carried out these missions for years, returning repeatedly to the same sites to swap out recording devices, all while avoiding Soviet naval patrols. The intelligence gathered was considered so valuable that the operation continued even after a spy, Ronald Pelton, revealed its existence to the Soviets. The Soviets, rather than immediately shutting down the compromised cables, sometimes left them operational, knowing they were tapped, and used them to pass disinformation. Cable tapping didn't end with the Cold War. Today, the NSA in the United States, GCHQ in Britain, DGSE in France, Unit 8200 in Israel, and other intelligence agencies within the Five Eyes alliance tap cable landings routinely. Not the deep ocean portions, which are difficult to access, but the landing stations where cables come ashore. This is where the data is accessible, where it can be collected in bulk. Documents revealed by Edward Snowden showed the enormous scale of these operations, with agencies collecting vast amounts of data flowing through international cables. The legal and ethical questions around this surveillance are complex and contentious. But, from a technical standpoint, cable landing stations are logical targets. All the data funnels through these points. Access is easier than trying to tap cables on the seafloor, and the sheer volume of information flowing through provides intelligence value that's hard to overstate. But sometimes, cables aren't tapped. They're simply cut. And whether these cuts are accidents or deliberate sabotage is often difficult to determine. In 2013, Egypt experienced a cable cut that dropped internet speeds throughout the country by 60%. 60%. It crippled businesses, disrupted communications, caused widespread frustration and economic damage. The official explanation was that a ship's anchor had damaged the cable. But the timing, the location, the political context, all raised questions about whether it might have been deliberate. Yemen, in 2017, experienced cable cuts that reduced internet capacity not just in Yemen, but hit Saudi Arabia with a 70% reduction in connectivity. Again, officially attributed to ship activity or perhaps to the ongoing conflict in the region. But the strategic implications were clear. Cut the right cables, and you can digitally isolate entire nations. More recently, Ukraine's experience in 2022 demonstrated how vulnerable modern nations are to cable disruption. When Ukraine lost cable connections, particularly in the early days of the conflict, it exposed Russian vulnerabilities as well. Both nations discovered how dependent they'd become on international connectivity. How much of their communications infrastructure assumed those cables would always work. Military operations, civilian communications, economic activity, all disrupted by damage to critical cable infrastructure. The Baltic Sea has become a focal point for cable security concerns. In 2024 and 2025, fears of Baltic cable sabotage rose significantly. Multiple incidents of cable damage, some under suspicious circumstances, have heightened tensions. The Baltic is surrounded by NATO members and Russia, a region where undersea cables carry enormous amounts of data between Scandinavia, the Baltic states, and the rest of Europe. Any disruption here has immediate geopolitical implications. The pattern of damage, the locations, the timing. Analysts study these incidents, trying to determine intent. Was it an accident? Was it probing? Testing defenses and response times? Was it a warning? A demonstration of capability? The ambiguity itself becomes a weapon. Nations can damage cables in ways that might be deniable, that might look like accidents, creating uncertainty and tension without quite crossing the threshold into overt attack. China has been particularly active in mapping Pacific cables and, according to intelligence reports, simulating cut scenarios, understanding exactly where cables run, where they're vulnerable, which ones carry the most traffic, which cuts would have the greatest impact. This is valuable strategic information. In any future conflict, the ability to disrupt an adversary's communications by cutting undersea cables could provide significant advantages. And the fact that such mapping and planning is happening during peacetime is itself concerning to many security analysts. The reality is that cables are now considered critical military infrastructure by virtually every major nation. They're not just civilian communications systems. They're arteries carrying military communications, intelligence data, command and control signals. Protecting them has become a national security priority. Knowing how to disrupt an adversary's cables has become part of military planning. Some nations have established special naval units tasked with cable protection. Submarines patrol areas where important cables run. Sensors monitor for unusual activity near cable routes. International agreements attempt to establish norms around cable protection, but enforcement is difficult and the legal frameworks are often ambiguous, especially in international waters. The vulnerability is real and growing. As more of our critical infrastructure becomes networked, as more military operations depend on data connectivity, as more of the economy moves online, the incentive to target cables increases, and the cables themselves remain fundamentally vulnerable. They're in international waters where sovereignty is unclear. They're too long to guard every meter. They're relatively easy to damage if you have the right equipment and the will to do it. We've created a global nervous system, a network of fiber optic cables carrying the thoughts and communications of our entire civilization. And like a biological nervous system, it has critical pathways, vulnerable points, places where damage can cause cascading effects throughout the system. We depend on this network more each year, yet it remains exposed, lying on the ocean floor. protected mainly by international norms and the difficulties of operating in the deep ocean. There's no easy solution. You can't militarize the entire ocean floor. You can't put guards on every cable. You can build redundancy, which helps but doesn't eliminate the vulnerability. You can develop better detection systems to identify cable damage quickly. You can maintain rapid repair capabilities. You can establish international agreements and consequences for deliberate cable damage. But ultimately, these cables remain one of the great strategic vulnerabilities of the 21st century. As you drift toward sleep tonight, consider the paradox. The same cables that connect us, that enable global communication and cooperation, that make our modern world possible. These same cables are also potential weapons, tools of espionage, strategic targets in conflicts between nations. The infrastructure of our connected world is simultaneously a bridge and a battlefield, and it rests on the ocean floor, vulnerable and essential, carrying our digital lives through the darkness below. We've talked about human threats to undersea cables, about war and espionage and accidents. But humans aren't the only ones interacting with these cables. Nature itself, in all its variety and unpredictability, creates challenges that engineers never fully anticipated. Let's explore the unexpected ways that the natural world encounters these artificial structures on the ocean floor. Sharks bite cables. This sounds almost absurd, like something from a tabloid headline, but it's a real and recurring problem. Possibly due to electromagnetic fields generated by the cables, sharks are attracted to them and sometimes bite into the protective layers. Sharks have specialized organs called ampulla of Lorenzini that can detect extremely weak electrical fields. They use this sense to hunt, detecting the tiny electrical signals generated by the muscle contractions of prey buried in sand. The electromagnetic fields around undersea cables, created by the high-voltage power running through the copper conductors to energize the repeaters, may trigger this hunting response. Or perhaps the sharks are simply curious, investigating this unusual object in their territory. Either way, shark bites have damaged cables, creating failures that required expensive repairs. The tooth marks are unmistakable when damaged cable is recovered. The distinctive triangular punctures of shark teeth, sometimes penetrating through multiple layers of protection. In response, engineers added Kevlar armor to cables in areas where shark activity is high. Kevlar, the same material used in bulletproof vests, provides a tough layer that shark teeth can't easily penetrate. It's a remarkable solution, protecting undersea cables from one of the ocean's apex predators using the same technology that protects soldiers and police officers. The interaction between cutting-edge telecommunications technology and ancient predatory instincts is almost poetic. But sharks aren't the only marine life affected by cables. The electromagnetic fields don't just attract sharks. They attract lobsters and other marine life as well. Studies have shown that some species congregate near cables, perhaps drawn by the M fields, perhaps attracted by other organisms that the fields have drawn in, creating a cascade effect. The cables become, inadvertently, gathering points for marine life. In some regions, cables have begun to act as artificial reefs. Marine organisms settle on the cable's surface. Coral polyps attach and grow. Fish use the cable as shelter and as a hunting ground. Over years and decades, a cable can become encrusted with life, transformed from a human artifact into something that functions as part of the marine ecosystem. This wasn't intentional, but it's happened nonetheless. Some environmentalists see this as a positive effect, creating habitat in areas that might otherwise be featureless sand or mud. Others worry about the unintended consequences of altering marine ecosystems in ways we don't fully understand. The ocean floor itself is not static, and this creates ongoing challenges. Sand waves, those underwater dunes created by currents, can expose cables over time. A cable that was buried 2 meters deep when it was installed might find itself gradually uncovered as sand migrates away. The cable becomes exposed, vulnerable to damage from fishing gear or anchors, at risk of being moved by strong currents. Regular surveys track this sand movement, and additional burial or protective measures are deployed when cables become exposed. Near Hawaii and other volcanic islands, internal tides create another challenge. These aren't the tides we see at the beach, the rise and fall of water level. Internal tides are waves that occur within the ocean itself, at the boundaries between water layers of different densities. These internal waves can be enormous, hundreds of meters in amplitude, and they flex cables daily as they pass. The cables must be designed with enough flexibility and slack to accommodate this constant movement without developing stress fractures. It's a wear factor that accumulates over years, a slow mechanical fatigue that must be accounted for in the cable's design life. In Arctic and subarctic regions, a different and more dramatic threat exists. Methane clathrate destabilization has snapped cables. Methane clathrates are ice-like structures formed when methane gas is trapped in water ice under high pressure and low temperature. They exist in vast quantities in Arctic seafloor sediments. But when conditions change, when temperature rises or pressure decreases, these clathrates can suddenly destabilize, releasing huge volumes of gas. When this happens near a cable, the released gas can trigger underwater landslides or create zones where the sediment loses all strength and flows like liquid. Cables caught in these events can be stretched, torn, or buried. The destabilization can be sudden and violent, with no warning. And climate warming increases the risk of these events. As Arctic waters warm, as seafloor temperatures rise, the stability margins for methane clathrates narrow. Areas that were stable for thousands of years may become unstable within our lifetimes. Climate change affects cables in other ways, too. Warming increases landslide risk more generally, not just in areas with methane clathrates. Seafloor sediments that have been stable can become unstable as temperatures and ocean chemistry change. Glacial melting increases sediment flows into the ocean in some regions. Storm intensity appears to be increasing, which means stronger currents and more powerful forces acting on cables and seafloor sediments. But cables also affect the environment. When they're installed, when trenches are plowed and cables are buried, the seafloor is disturbed. Marine habitats are damaged. Organisms that lived in that sediment are displaced or killed. This raises legitimate environmental concerns. How much damage does cable installation cause? How long does recovery take? Research on this question has produced some reassuring findings. Posidonia seagrass, a critical Mediterranean ecosystem engineer, recovers after cable trenching. Studies tracking trenched areas over time have shown that seagrass gradually recolonizes the disturbed sediment, eventually restoring the habitat. The recovery isn't instant. It can take years. But it does happen. The ecosystem proves resilient. And when compared to other human activities in the ocean, cable installation looks relatively benign. The environmental impact is smaller than bottom trawling, the fishing practice where weighted nets are dragged across the seafloor. Bottom trawling happens constantly across vast areas, repeatedly disturbing the same seafloor year after year. Cable installation happens once, along a narrow corridor, and then the cable remains essentially static for decades. The footprint is small, the disturbance temporary. This doesn't mean cable installation has no environmental cost. It does, Every activity humans undertake in the ocean affects the environment to some degree. But in the hierarchy of marine impacts, undersea cables rank relatively low. The benefits they provide, enabling global communication and digital connectivity, arguably outweigh the modest environmental costs of their installation. There's something humbling about these interactions between human technology and nature. We engineer these cables with such precision, such sophistication. We control the wavelengths of light to a fraction of a nanometer. We tune the refractive index of glass to incredible precision. We manage signals with exquisite care, and then a shark bites the cable because it's curious. Or a sand wave migrates and exposes what we carefully buried. Or methane trapped in ice for millennia suddenly releases and tears apart our carefully laid infrastructure. Nature operates on timescales and magnitudes that dwarf our engineering. The ocean is vast, powerful, ancient, and unpredictable. We place our cables in this environment and hope they'll survive, protecting them as best we can, repairing them when they fail, adapting our designs to account for threats we discover. It's an ongoing negotiation between human intention and natural reality. The cables rest on a seafloor that's constantly changing, in water that's never still, surrounded by life that doesn't understand or care about the human purposes these cables serve. And yet, most of the time, they work. The light pulses flow, the data travels, the connections persist. Our technology proves robust enough to survive in this challenging environment, at least most of the time, at least for decades at a stretch. As you settle into sleep, imagine those cables down there in the darkness. Sharks swimming past, perhaps pausing to investigate with a curious nudge or exploratory bite, only to encounter Kevlar armor that resists their teeth. Lobsters gathering nearby, drawn by electromagnetic fields they can sense but not understand. Seagrass slowly growing back over trenches dug years ago, nature reclaiming what was temporarily disturbed. Internal tides flexing the cables in their slow, powerful rhythm. And through all of this, the light continues to flow. The data continues to travel, connecting continents despite everything the ocean can throw at these thin lines of fiber and steel. We've journeyed through history, through physics and engineering, through the challenges of nature and humanity. Now, as we near the end of our exploration, let's look forward. What does the future hold for these cables that connect our world? What innovations are emerging? And what does it all mean for how we stay connected in the decades to come? The hunger for bandwidth never stops growing. Every year we send more data, stream higher resolution video, connect more devices, build more services that depend on fast, reliable internet connections. And so engineers continue pushing the limits of what's possible through a single cable. Space division multiplexing is one of the most promising advances, boosting fiber pairs to 25 or more per cable. Instead of just packing more wavelengths into a single fiber space division, multiplexing uses multiple fiber cores within what appears to be a single strand or arranges fibers in new, geometric patterns that allow more of them to fit in the same cable diameter. Each fiber becomes a separate spatial channel, and combined with wavelength division multiplexing on each fiber, the total capacity multiplies dramatically. A cable that once might have carried a few terabits per second can now carry tens or hundreds of terabits, all flowing through the same physical space. But capacity isn't the only concern. Security grows more important each year as more critical communications flow through these cables. Quantum key distribution is being tested for security, a technique that uses the strange properties of quantum mechanics to create encryption keys that are theoretically unbreakable. Any attempt to intercept the quantum signals used to generate the keys disturbs them in detectable ways, alerting both parties that someone is listening. Implementing quantum key distribution over transoceanic distances presents enormous technical challenges. Quantum states are fragile, easily disturbed by the very processes that affect classical optical signals. But if these challenges can be overcome, the result would be cable communications that are secure against even the most sophisticated eavesdropping, protected by the laws of physics themselves rather than just mathematical complexity. The physical design of cables continues to evolve to slimmer fibers fit more capacity into the same diameter cable. By making the fibers slightly smaller, or by improving the materials around them, engineers can pack more fibers into a cable without making it larger or heavier. This matters because larger cables are harder to handle, more expensive to manufacture, and face greater hydrodynamic forces during installation. Every improvement in fiber density makes new cable installations more economical. But perhaps some of the most exciting advances involve not just transmitting data, but using the cables themselves as sensors. Distributed sensing detects vibration and strain in real time along the entire length of a cable. By analyzing subtle changes in how light propagates through the fiber, systems can detect when something is happening near the cable: an earthquake, a submarine landslide, a ship dragging anchor across the seafloor. This transforms cables from passive conduits into active monitoring systems. The same infrastructure that carries our communications can also watch over itself, alerting operators to potential problems before they become failures. And beyond self-monitoring, cables become scientific instruments, providing data about seismic activity, ocean currents, water temperature, and other phenomena all along their route. Acoustic monitoring improves fault prediction even further. By listening to the sounds in and around the cable, analyzing patterns of vibration and stress, systems can identify developing problems: a section of armor that's starting to fray, a splice housing where water is beginning to penetrate, a burial trench where the cable is being gradually exposed. The cable begins to tell us when and where it needs attention, allowing preventive maintenance instead of waiting for catastrophic failures. When problems do occur, artificial intelligence is transforming how networks respond. AI optimizes routing around failures instantly. In the past, when a cable failed, network engineers would manually reconfigure routes to send traffic through alternate cables. This took time, caused delays, sometimes led to mistakes. Now, AI systems monitor network health continuously, and when a failure occurs, they recalculate optimal routing paths in milliseconds, automatically redirecting traffic before most users even notice a problem. These AI systems learn from each incident, building models of network behavior, understanding which alternative routes work best under different failure scenarios, predicting how different parts of the network will respond to various disruptions. The network becomes intelligent, self-healing, resilient in ways that purely manual management could never achieve. Infrastructure planning continues to emphasize redundancy. New cable routes are chosen not just for efficiency, but to ensure that failures in one region can be compensated by capacity in another. New redundancy reduces outage impact dramatically. When there are multiple cables on diverse routes connecting the same regions, the failure of any single cable becomes an inconvenience rather than a catastrophe. Traffic redistributes, speeds might slow slightly, but connectivity persists. Building this infrastructure isn't cheap. Deployment costs reach $15 to $50 million per 10,000 kilometers. Depending on the route, the water depth, the seabed conditions, and the technology used, a major transoceanic cable system might cost hundreds of millions of dollars from planning through completion. These are massive infrastructure investments, requiring coordination between multiple companies, often multiple governments, and years of planning and execution. But despite these enormous costs, despite the complexity and challenges, one fundamental fact remains unchanged. Cables remain irreplaceable by satellites. We've talked about this before, but it bears repeating as we think about the future. Satellites have their place. Certainly, they're valuable for remote areas, for mobile communications, for regions where cables can't reach. But for the bulk data transfer that defines modern internet use, satellites simply cannot compete. The physics is unforgiving. The speed of light is finite. Signals traveling to and from satellites in geostationary orbit face unavoidable latency, the delay that makes real-time interaction difficult. Satellites in lower orbits avoid the worst of the latency but require elaborate constellations and handoffs between satellites as they pass overhead. The bandwidth available to satellites is limited by spectrum allocation and the realities of radio transmission. And the cost per bit transmitted remains far higher than for fiber optic cables. So barring some revolutionary breakthrough in physics or technology, the future of global internet connectivity remains rooted in cables on the ocean floor. They will continue to carry the vast majority of international data. They will continue to be where innovation happens, where capacity grows, where the infrastructure that matters most is built and maintained. And this brings us to a profound realization. The Internet's most important infrastructure lies unseen beneath the ocean. Not in data centers, though those matter. Not in the servers and routers and switches that we sometimes glimpse in photos or documentaries. The truly critical infrastructure, the irreplaceable foundation of global connectivity, rests in darkness and silence on the seafloor. Thousands of meters below the surface, largely forgotten by the billions of people who depend on it every day. These cables are marvels of engineering, achievements that rival any in human history. They embody decades of innovation in materials, science, optical physics, mechanical engineering, and information theory. They represent billions of dollars of investment and decades of accumulated expertise. They connect cultures, enable commerce, carry conversations, transmit knowledge, bridge distances that once seemed unbridgeable, and they're fragile. Vulnerable to nature, to accident, to deliberate harm. Protected primarily by their remoteness, by international norms of uncertain strength. By the vigilance of the small community of people who understand their importance and work to maintain them. As you drift off to sleep now, as your consciousness fades and dreams begin to form, hold this thought. Right now, at this very moment, light is racing through fibers beneath the ocean. Terabits of data every second, traveling at 200,000 kilometers per second, connecting continents, carrying the digital pulse of our civilization. The cables rest in eternal darkness, in cold and pressure and silence, doing their patient work. They've been there since before you were born. Some of them, they'll likely still be there long after tonight is forgotten. They're the hidden threads that weave our world together, the invisible infrastructure that makes our modern life possible. And now, as you know their story, as you understand something of what they are, and how they work, and why they matter, perhaps they'll seem a little less invisible. Sleep well, knowing that beneath the waves, the work continues, the light flows, the connections persist. The world stays linked, pulse by pulse, wavelength by wavelength, through the remarkable technology of undersea cables.